Okay, so what we're going to do now is continue section 4.9, where we were talking about uh, some special types of reactions and some sort of unique reactions. And today is kind of cool. It's going to be a application of using this Redox. These problems are pretty intense, and what we're going to do is uh, just going to introduce these videos, and I don't even want you to start the problems until tomorrow. We'll have a work day tomorrow to get the problems, and I'll assign some specific ones that we're going to be doing. So this will continue into next week. So what we're doing here is pretty intense. You might remember from last lecture that we sort of separated nitric acid from the other acids. There's kind of a cool demonstration I do where I put a penny in sulfuric acid, and if you kind of file the edges off a little bit, it'll eat out all the zinc that is inside. A penny is actually a zinc coated in copper. It'll eat all that zinc out from the inside and just leave the copper shell. But if you were to drop the penny into nitric acid, it disappears. They're both strong acids. They both have the hydrogen ions available. So what is the difference? Well, the difference is that this nitrate, nitrates tend to be very reactive compounds. They are the stuff of explosions, so having this NO3, this is certainly not explosive, but it will undergo and actually oxidize the metal itself when the hydrogen cannot, like copper. So if you look at this reaction, a solid copper penny, you drop it in nitric acid. So if we were to do that instead, you'd notice a couple of things. Number one, the first thing you'd notice would be this brown NO gas, nitrogen monoxide, coming out of there. It's a very dark brown and nasty gas. So this is something we would do in the hood. And you would also notice that the penny disappears. There's no more solids over here. There's just a gas that comes out as kind of a cloud, and then the penny is gone. And the zinc certainly reacts with the hydrogen, so as what we talked about yesterday, so the penny disappears. It's a way of losing a penny forever. So one of the things when you look at this reaction is you go, hey, it's not balanced. So then you go, well, I'm going to put a 3 over here, and then that will make 3 oxygens. And then you're like, whoops, now I only have 1 nitrogen over here, so I'm going to put a 3 there. Now we're up to 9. And you'd be like, if you look at this, this is impossible to balance using the technology that you have right now, which is just old trial and error, left to right, put in the coefficients. So therein lies the rub, and that is what we're going to learn today. How do you balance that which cannot be balanced? And the answer is actually quite intense, and involves several steps as to how we can do this. Circle this page, highlight it. This is the big 7. When you do these problems, I want you to follow this numbering system. So I know that you are following through each step. even the steps that didn't require change, I'm going to have you write them. Now, the key does not do it that way. So I want to be very clear that I'm going to expect 1 through 7 on the problems that you'll be doing in class tomorrow. So that's why we're going to set them up this way in our notes, and you're going to have these beautiful examples to use and follow through when you are doing these problems. Okay, so there's your impossible thing to balance. Well, you're going to do steps 1 through 5 on the reduction and then on the oxidation reaction. So to figure out what is what, use your oxidation numbers. So it's, I think, good to assign those left to right here. If you can't do it in your head yet, I just do these in my head, and I go, that goes from 0 to +2. That's up, that's Leo, and that is not the reduction part. So hopefully this one's something's being reduced. Oxygen -2, no change. Nitrogen is going to be a +5 over there to leave the 1- charge. So it goes from +5 down to +2. That's reduction. Okay, so therefore the part that I write in step 1 is to say NO3 minus aqueous turns into NO. That's the reduction reaction. Okay, now just going back quickly, step 2 says balance all atoms except for oxygen and hydrogen. Oxygen and hydrogen are the key things to get balanced here. That nitrogen is already balanced, and this is the example of what I was telling you about, that even though there is no change from there to there, I still want you to rewrite the equation with all the little AQ symbols and charges, attention to detail. We're going to do quality over quantity on this assignment. Okay? You're just going to have a few problems to do during class and a lot of time to work on them. So I want just really nice, perfect problems. So then you go, okay, now what's step 3? And you keep referencing this. I'll just keep clicking back to it here. Now you balance oxygen by adding H2O molecules. Okay? So how do we do that? Well, the oxygen, there's 3 over there, so I can just add 2 H2O molecules. Now these are aqueous solutions, so liquid will always be the form that you use for H2O. So there's your NO3 minus your NO. Now the oxygens are balanced. But what did you screw up? You screwed up the hydrogen. You got 4 hydrogens over there and 0 hydrogens over there. So I'm guessing maybe that's step 4. Ooh, balance for hydrogens by adding H+ ions. How do we know we have H+ ions available? That's the key to what it says up here, that these are acidic solutions. So because of that, we now have enough hydrogens available, and as you can see, I got to have 4 H's to balance that, and usually you put the water and the hydrogen after the principal products here. So now you have an equation where all the elements are balanced, and that's how you balance the impossible, by saying, well, it's a acidic aqueous solution, so I have H+ to add and I have water to add. There is a problem though. Something in here is not balanced. If you look, here's a negative and 4 positives. So a negative on this side and 4 plus charges. So what you have to do in step 5, and again just go back quickly here, is to balance the charge by adding electrons. Well, remember, this is a reduction reaction. So a reduction reaction, that's going to give you the hint that you need to put the electrons on this side. It's gaining those electrons. How many does it gain to balance what's on the right side? Well, on the right side, there's absolutely no charge at all. On this side, 4 pluses, 1 minus, that's a total of 3 pluses. How do I get rid of that? By adding electrons on that side? I add 3 electrons to the equation. All right? So now that's going to be step 5. All right? So we now have completed, we're not even halfway through the problem, so you can see that these are a doozy. This is definitely a top 10 AP chemistry problem, is balancing redox and acidic, and then we're going to go to basic solutions next week. But we'll focus on acidic this week. All right, so that's only for the reduction portion. So now we got to do the oxidation half reaction. So by process of elimination, that means you got the copper going to the copper plus 2. All right. Step 2 was to balance all the other ions. And again, what you're going to notice on this one is you're just going to rewrite this so that I know that you are following the steps. Okay? This is going to seem like overkill on a problem like this, but for this first assignment, I want steps 1 through 5. Now, step 3 was to balance the oxygens. There are none, so nothing to do there. Take your time, write down this good example so you can follow this format, and so that you can remind what you're doing. I think it's a good idea to write in this thing as well. Pause when needed. And then now balance the hydrogens, which of course doesn't apply as well. So, yeah, I'm going to ask for this first assignment that you write that 4 times, even though you didn't change anything, just to get through the step-by-step process so that we can get really, really good at these. Now, this is oxidation, so I know the electrons have to go on this side. Well, we're heavy on the pluses on that side, so that's good. If you're not, you did something wrong. And so that means I got to put 2 electrons over there on the right side. Okay? So, that will get you your oxidation half reaction and your reduction half reaction. And I'm going to stop this video here because the next step is pretty involved and we won't finish it in a minute and a half, and that's all I have left. So you are now going to go on to video number 2.